Hi, George Diamond here. Welcome to video number 2 on extreme values of functions. Now in our textbook, this is section 3.1, and this is our second video. Now the first video we introduced some vocabulary. We talked about relative and absolute, maximum, minimum, so you can go back and look at the first video to see some of the vocabulary and where we talked about some of that stuff. Now in this video we're going to look at examples. Now the first example we're going to look at is make sure we know how to find the critical numbers of a function. Now remember now, if you look at a function, okay, maximum and minimum points only occur at the critical numbers in the interior of a function. Now on a closed interval, the endpoints can be maximum and minimum points. But if you have a maximum and minimum point in the interior of a function, they only occur at the critical numbers. So it's very important in calculus that we be able to find the critical numbers. Now, so we're going to run through a couple examples just to make sure we can find the critical numbers. Then we'll do a couple examples where we actually find the absolute minimum, absolute maximum of the function. So let's start off with example number 1. This is f of x equals x to the 4th minus 8x squared. Now I'm going to copy that problem down over here, and then I'm going to pull this one, and we're going to take this off. Right, so number 1, we'll find that the critical numbers, and this is f of x equals x to the 4th minus 8x squared. All right. Now, let's see if we can find the critical numbers of this particular function. All right, so let's see what they would be. Now, a couple things you got to remember now about critical numbers. So critical numbers only occur where the derivative is equal to 0, okay, or where the derivative does not exist. When we talk about the critical numbers, okay, we're looking for those points on the curve where the derivative is equal to 0. Now, if the derivative is equal to 0, derivative is slope. So we're talking about a horizontal tangent line to the graph. So that's what we're looking for. So if we find the derivative equal to 0, we set it equal to 0, we find those x values. We're finding the numbers where the slope of your tangent line is 0. Or it could be where the derivative does not exist. So D and E indicates the derivative doesn't exist. So it could be that the graph comes to a corner or a cusp of some type. Right, so we have to check both of those, right, to indicate where our critical numbers are at. So that's what we're getting at. I got to get our derivative, and then we want to check to see where the derivative equals 0 and where the derivative does not exist. So let's start off by getting our derivative here first. Now to find the derivative of x to the 4th minus 8x squared, so this is a pretty easy example. Just a little polynomials, those are pretty easy to do. Now the derivative of x to the 4th is 4x cubed minus, now the derivative of negative 8 minus 8x squared would be minus 16x. So this is our derivative. Now remember, now we're looking for, and we need to find where the derivative is equal to 0, and we're going to look where the derivative does not exist. So two things. Okay, where the derivative equals 0 and where it doesn't exist. Now, okay, first thing you notice about the derivative is a polynomial. So polynomials are defined everywhere. So when you talk about where the derivative doesn't exist, there's not any. So any kind of polynomial is continuous everywhere. So it's there are no places where a polynomial does not exist. Same is true for sine and cosine. So if your function has sine and cosine, it's going to be it should be any place where the derivative doesn't exist, unless it's in the bottom of a function of a fraction. Now, where the derivative is equal to 0 now, let's take the actual derivative and set it equal to 0. So 4x cubed minus 16x now. Now, we have to solve this equation for x. Now, to solve it for x, that means put it in factored form and then actually solving the equation. All right, so with this particular function now, we got this our derivative. So 4x to the 3rd minus 16x. Okay, let's factor off our common factors. So 4 and 16, we have a common factor 4 and x. Let's see what we have left remaining inside our parentheses now. So factoring the 4x off the first term gives us x squared minus 4. Okay, now let's finish factoring this. X squared minus 4, this will factor as 4x times x plus 2 times x minus 2. All right, so we're looking more, so let's take the 4x, set this equal to 0, x plus 2 equals 0, and x minus 2 equals 0. And as you solve these, okay, you end up with x equals 0 here. That'll be our first critical number. Okay, the second critical number would be x equal negative 2, and the third one here would be x equal positive 2. So there are three critical numbers here, 0, -2, and +2. So we're talking about where the derivative, so at each of these points, really, you could have a place where, it could be a possible minimum or maximum point. At x equals 0, x equals -2, x equals +2. So possible minimum or maximum. Now to actually check that with the function like this, you have to do some more to it, but this will get us started. Make sure we can find the critical numbers of a function. They got 3 critical numbers here, 0, -2, and +2. Okay, let's try another example. So let's try another one. So as I said, polynomials are pretty easy to do. As long as you can factor them, okay, you're going to be in good shape. Okay, let's try this problem right here. So problem number 2, we'll go ahead and set it up here. Now, in just a moment, I want to take this down, all right, so we give me a little bit more room to work. But we're going to see if we can find the critical numbers of, this will be problem number 2. And we got f of x is equal to, this will be 4x over x squared plus 1. All right, now, once again, we're just finding the critical numbers. That's all we're doing. So to get us started, now to begin with, we got to get our derivative. Now this is a fraction. That means the quotient rule. All right, so now let's see what we get for our derivative here. All right, so the derivative, this will be x squared plus 1 squared, so the bottom squared, and then the bottom, so x squared plus 1 times the derivative of the top, and the derivative of 4x is 4, minus the top, which is 4x, times the derivative of the bottom. Now the derivative of x squared minus 1 is 2x. Now, this is our derivative. Now, let's see if we can simplify it a little bit. I'm going to move this out of the way. All right, let's see if we can simplify the derivative sum. So we simplify this. Okay, this will be x squared plus 1 to the second power. Multiplying 4 inside our parentheses here gives us what? 4x squared plus 4. Okay, minus 8x squared. Okay. Combine like terms, and our derivative becomes, so x squared plus 1 to the second power. Combining the x squared terms in our numerator gives us what? 4 minus 4x squared. So this is our derivative now. So this is our derivative. So 4 minus 4x squared, all this over x squared plus 1 to the second power. Now, to get our critical number, now we're working where the derivative is equal to 0. And where the derivative does not exist. So you got to check both of these. Right now we got a fraction, so we got to kind of watch out with this problem here. Okay, first of all, let's see if we can figure out where the derivative doesn't exist. Now, if your derivative is a fraction, remember, the bottom of the fraction cannot equal 0, all right? So it won't be defined. So we got to find the zeros of the denominator. So let's take just the denominator only. We're going to set it equal to 0. So let's take we'll come over here. So x squared plus 1 to the second power. Let's set that equal to 0. So where the derivative doesn't exist will be where the denominator of the derivative would be equal to 0. Now, as you solve this for x, we're going to get rid of the square by taking the square root of both sides. That gives us x squared plus 1 equals 0. That means that x squared is equal to -1. When you take the square root of both sides, that gives x is equal to plus or minus the square root of -1. Now, the square root of -1 is imaginary. That indicates no solution. Right? So no solution here. So no solution. So square root of -1 is an imaginary number, so there are no places where the derivative is equal to 0. Now, let's check to see where the derivative, so there are no places where the derivative does not exist, so that's, so we have to worry about that. Now let's see if we can get where the derivative is equal to 0. Now to find the zeros of the derivative, this time we're going to take the entire derivative, so the entire derivative, and let's set it equal to 0. So now we're going to have 0 equals 4 minus x squared, 4 minus 4x squared. Get all this over x squared plus 1 to the second power. So now to get where the derivative is equal to 0, you take the entire derivative, set that equal to 0, and set up your equation. Now remember now, when you're figuring out where the derivative doesn't exist, you take the bottom of the derivative, just the denominator. But where the derivative is equal to 0, you've got to take the whole derivative and set that equal to 0. Now, to start off, I said we're going to break this fraction up, so we're going to multiply x squared plus 1 squared on this side, and it's going to cancel out with the denominator. We're going to multiply x squared plus 1 squared to the right-hand side. Now, x squared plus 1 squared times 0 gives us 0, and that's equal to 4 minus 4x squared. Now, we get to solve this equation for x now. So add 4 to both sides, that gives us negative 4 equals negative 4x squared. Change the signs, divide both sides by 4, that gives us 1 equals x squared. Bring this up here. So take the square root of each side, so the plus or minus the square root of 1 is equal to x. That means that plus or minus 1 is equal to x. So plus or minus the square root of 1 is equal to x. So we have two critical numbers, right? X equal negative 1 and x equal positive 1. So two critical numbers, positive 1 and negative 1. That means we have two possible candidates that could be maximum or minimum values within an interval or on the graph. So if this were a closed interval, we would have two possible candidates that could be maximum or minimum points, whether they're absolute or relative max or minimums, but two numbers. So there were no values where the derivative doesn't exist. So in this case right here, where the derivative equals 0, it would be at negative 1 and positive 1. So two numbers there, two critical numbers where we could possibly have a maximum relative or absolute maximum or minimum points. Okay, let's try another example. That was example number 2. Now we're going to work these pretty quickly to kind of save time on our video. So let me erase this. All right, so example number 3. Okay, let's do one more example, and all we're going to do again, we're just finding the critical numbers. When you're doing any type of maximum or minimum problem in calculus, and typically it's going to start off, finding your critical points, or your critical numbers, right? So that's why we're going to do a couple of these just to make sure we know how to do these. So let's bring up example number 3. All right, so here's our third example. Okay, let's try a trig function. All right, so example number 3, this will be, so number 3, we've got h of x is equal to, now this will be 2 sine x minus cosine 2x. How do we get the critical numbers of this type of trig function? Now, to get us started, first thing we want to do, let's find our derivative. All right, so let's find our derivative. Now, the derivative here would be, now let's start off, let's get the derivative of sine x. Now, the derivative of sine x is cosine, so it would be 2 cosine x. Let's see, now the derivative of cosine 2x, now this is negative cosine 2x. This would be minus. Now, as you take the derivative of cosine 2x, we have to use the chain rule. The outside part of the function is cosine. The inside part of the function is 2x. So we got to use the chain rule to take this derivative. Now, the derivative of cosine is negative sine. So it would be negative sine. Now, remember, when you do the chain rule, you take the derivative of the outside, leave the inside the way it is, times the derivative of the inside. So times 2. So that would be the derivative of cosine 2x. Now you end up here with minus a negative, which becomes plus a positive. So it's going to be a positive sine 2x. Now I'm going to move the 2 to the left-hand side over here. So we end up with plus 2 sine 2x. Okay. Now, in order to solve this equation here, well, first of all, let's take a look at so we get our derivative. We got to know where the derivative is equal to 0 and where the derivative doesn't exist. So where the derivative h prime would be equal to 0, and where would h prime not exist? Where does it not exist? Right. Now, first of all, the derivative is all in terms of sine and cosine. Sine and cosine are defined everywhere. So this is the easy part. So there are no values where the derivative doesn't exist. All right. Now, let's see where the derivative is equal to 0. So let me take this and set it out of the way. Let's see where the derivative is equal to 0. So I'm going to do 0 equals 2 cosine x, okay, plus 2 sine 2x. And I'll erase this from here. So there are no places where the derivative is undefined, right? That's where it doesn't exist. Now, to solve this equation, this trig equation, okay, there's a couple of ways to do this. Probably the easiest way would be to rewrite sine 2x. Now, if you remember what's called the double angle formula in trigonometry, okay, sine 2x, or sine 2, we'll see, sine 2x is going to be equivalent to, okay, 2 sine x cosine x. We can rewrite sine 2x in terms of just sine and cosine. So this is equivalent to 2 times sine cosine x, 2 sine x cosine x. Now, we already have a factor of 2 here. So I'm going to take this right here, and we're going to substitute it in over here now. All right, that gives us 0 equals 2 cosine x, okay, plus. Now, we already have a 2 here, so it'll be 2 times 2 gives us 4 sine x cosine x now. So rewriting it, this will be a lot easier, at least a lot easier for me to solve. So there's probably more than one way to do this type of problem, but that's probably the easiest way to rewrite the sine 2x as 2 sine x cosine x. All right. Now, to finish solving this, first thing you want to do is factor. All right, so let's factor it out. Now you got a common factor of 2, also cosine. So 2 cosine x is our greatest common factor. Factoring 2 cosine x off the first term gives us 1 plus. Factoring 2 cosine x off 4 sine x cosine x gives us 2 sine x. So you put it in factored form, and this is what we get. All right. Now, as you solve this equation, that means 2 cosine x is going to be equal to 0. Okay, or 1 plus 2 sine x is going to be equal to 0. Okay, now let's solve the first one. Divide both sides by 2 gives us cosine x is equal to 0. So 0 divided by 2 gives us just 0. So the cosine x is equal to 0. Now if you remember the unit circle, the cosine is equal to 0 here at pi over 2. And this is 0, 1, and down here at 3 pi over 2 at 0, negative 1. So cosine, remember, as you get your order pair, this is cosine. Okay, this is sine. The y value is sine. The x value is cosine on the unit circle. All right, so this first part of the equation, all right, so x is equal to pi over 2. X is equal to 3 pi over 2. So we've got two critical numbers from our first equation. Now let's solve the second equation for x also. Subtract 1 from both sides here gives us 2 sine x equals negative 1. And then dividing by 2, you'll end up with sine x equals negative 1/2. So where is sine equal to negative 1/2? Now if you remember the unit circle again, as you remember your unit circle. Okay, let me go and sketch our unit circle up here. The y value, sine is y, so the y value would be negative 1/2 here. Okay, this is negative 1. All right, so that would put the point here, 1 point here, and then 1 point over here. Now this point here would be 7 pi over 6. Now that'll be the negative square root of 3 over 2 and negative 1/2. So 7 pi over 6 is going to be one solution. The other solution will be over here at 11 pi over 6. Now this is the square root of 3 over 2 and negative 1/2. So 2 places on the unit circle, right, where sine x is equal to negative 1/2. So actually I should have included the restrictions on the domain. This problem is just from 0 to 2 pi only. So from 0 to 2 pi, I didn't indicate that on the problem, but they have a restriction on it. So with this particular equation, then you have x is equal to, so we say 7 pi over 6, and x is equal to 11 pi over 6. So we have, count them, 4 critical numbers. Pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. That's how you get the critical numbers on a trig equation or a trig function like you see here. Okay, just like you would any other equation, find your derivative, and then as you set it equal to 0, you put it in factored form, and then you got to be able to solve that type of trig equation. Right? So 4 critical numbers. Now remember, each of these numbers could be a possible relative or absolute minimum or maximum on a curve. Right? So it could be one or the other. Okay, so this is 3 examples as to how to find critical numbers. Now the next example, we're going to look at finding absolute extrema on a closed interval. So let's take a look at problem number 4. So let me erase this here first. So let's take a look at problem number 4. So finding relative extrema on a closed interval. All right. Here we go. So here we go. We'll start off with an easy problem. This is just a little polynomial function again, 3x to the 4th minus 4x cubed. Okay, let's see what the let's see if we can find the. Now we're looking for the absolute extrema. That is the absolute minimum, absolute maximum point on this closed interval from -1 to 2. -1 is part of the domain, 2 is part of the domain, so you're talking about solid, solid dot basically at each endpoint here. So anytime you see a closed interval like this, so it's closed, you're looking for minimum or maximum. The minimum or maximum values can be at the endpoints. So remember now, on a closed interval, as long as the function is continuous, this is a polynomial, it's continuous everywhere, there has to be a minimum, an absolute minimum, and an absolute maximum. So we're going to find both of them. Now, it could be that the minimum or maximum point could be at the endpoints, okay, or it could be in the interior of the function. Now, the interior of the function would be its critical numbers. All right, so let me go ahead and copy our problem down here. So this is number 4. Now we're looking for absolute extrema this time on the closed interval. Now, we got f of x is equal to 3x to the 4th minus 4x cubed. And our interval is from -1 to 2. All right, so -1 to 2. All right, so let's start off probably to begin. Let's go and get our derivative, right? So we'll get the derivative. Now the derivative here would be 12x to the 3rd minus 12x squared. So here's our derivative. All right. Now to begin, so this is a closed interval, so I like to start off by finding the endpoints first. So let's get our endpoints. Okay, let's check our endpoints. Now to get your endpoints, all we got to do now is take each of your endpoints, substitute it into your function, and that'll give us the y value. Now the y value is actually going to be the maximum or minimum value, all right? And the maximum or minimum value will occur at, maybe x equal -1 or x equal 2. All right, so let's take the -1 first, plug it in. So the function at -1. Now substituting -1 in for x gives us 3 times -1 to the 4th power minus 4 times -1 squared. All right. And let's see, what do we get here? Now this would be 3 minus 4. So that'd be a positive minus 4 gives us -1. Now, so as you look at this particular point now, we're talking about the point -1, -1. All right, so that'll be our first, that'll be the value at our first endpoint there. So -1, -1. Well, actually, so -1, this will be a -4. Squared, so that's correct. Actually, I'm sorry, this should be to the 3rd power. So this should be 4x to the 3rd power here. This would be -1 to the 3rd. Now that's going to change my answer here. So let me go and make that change if we could. This would be 3 minus a -4, which makes this plus a +4, which is 7. So the actual value here is going to be +7. So it'll be a -1, 7 will be that's going to be the location of one endpoint. Now the actual minimum or maximum value would occur at 7. So 7 is the highest or lowest point, as you look at the y-axis there. Okay, let's try the 2. This will be f of 2. So the function of 2 would be 3 times 2 to the 4th power minus 4 times 2 to the 3rd power. And let's see, what do we get here now? This would be 8. This would be minus 32. And this would be 2 would be what, 48. Minus 32, which is 16. So 16, this would be the point 216. Right. So the other endpoint is located at 216. Okay, so one endpoint's at -1,7, the other endpoint is at 216. Now we've gotten the 2 endpoints. Now notice, the 2 endpoints. The first endpoint is the y value is 7. The second endpoint, the y value is 16. So just looking at the endpoints only, 16 would be the maximum, 7 would be the minimum. So if you're just looking at the endpoints, okay, that would be the maximum minimum. So you want to check the y values and compare the y values. So let me take this down. We need to check our critical numbers. All right, so next, let's check our critical numbers. So our critical numbers. Remember, the critical numbers always occur when the derivative is equal to 0 and when the derivative does not exist. All right. Now, immediately you recognize the derivative is a polynomial, so there is no place where the derivative doesn't exist. So the derivative does not exist, there is none. So this is none. So there are no values where the derivative doesn't exist. So let's find the zeros of the derivative. So now you're going to take the derivative, set it equal to 0. So that 0 equals 12x cubed minus 12x squared. Now, to solve this type of equation, you got to put it in factored form. So let's factor this. So 12x, we can factor the 12x off. That will give us, actually we can factor 12x squared off. So we take x squared off each term, and that will give us x minus 1 remaining inside our parentheses. Now, let's take each of these factors and set them equal to 0. Now, 12x squared equals 0. We'll take the x minus 1, set that equal to 0. So, dividing by 12 gives us x squared is equal to 0. Take the square root of both sides, we end up with x equals 0. There you go. Our first critical number is 0. Now, the second critical number will be positive 1, so x equals 1. So, two critical numbers, 0 and 1. All right. So, 0 and 1. Now, once you get your critical numbers, we need to see what the y values would be. So we can compare the y values to the 16 and the 7. All right, so we got our critical numbers, we got our derivatives, so you can see what we did here. I'm going to erase a little bit to give me a little bit of this to give me a little bit more room. Now, one thing you got to check, I didn't mention this before, but when you get your critical numbers, make sure that 0 and 1 are in fact within your interval. All right, 0 and 1 is between negative 1 and 2, so we're good with these two numbers. So make sure that they are within your intervals. All right, so our critical numbers, so we got x equals 0, x equals 1. All right, now, just like we did the endpoints over here, let's take the 0 and the 1, so one at a time, and let's substitute each of those into the original function. Now be careful now. We're not substituting into the derivative. You're going to put them back into the original function. Because remember now, we have to compare their y values to get the absolute maximum or minimum points. Let's do the 0 first. So the function at 0 would be 3 times 0 to the 4th minus 4 times 0 cubed, which is 0. So one critical point will be at 0, 0. So that's the actual location of the critical point within the interior of the function. So there would be a horizontal tangent line at the point of 0, 0. Let's do the other endpoints. This would be f of 1. Okay, this will give us 3 times 1 to the 4th minus 4 times 1 to the 3rd. And this is what? 3 minus 4, which is negative 1. So the other endpoint will be 1, negative 1. Okay. All right. Now, let's compare. So remember now, we're comparing the y values, 7, 16, 0, and 1. Okay, remember the smallest is going to be the absolute minimum. The greatest is going to be the absolute maximum. So as you look at these, let's see, first, the maximum would be 16. That's our maximum. Now the minimum would be at negative 1, 7, so it looks like this, here's the minimum value here. So one of your absolute minimum occurs at a critical point on the curve, right? So it's going to be at 1, negative 1. And the maximum value occurs at the right endpoint. Okay, so this will be your maximum. 1, negative 1 is going to be our minimum. So just remember, once you get your critical numbers now, you got to substitute them back up into the original function. You don't want to substitute them into the derivative, right? But back into the original function. Right. Let's try another one. That's just a little polynomial example, so pretty easy. We start off with an easy one, and these are going to get a little bit harder. We're going to look at 2 more examples. Let's try another one here. Let's try example number 5. So example number 5. So example number 5, let's try this problem right here. This is 2x minus 3x to the 2/3 power. Okay, over the interval from negative 1 to 3, let me make sure I got the problem copied down correctly. Yes, all right, we're ready to go. Okay, let me write the problem over here. This is number 5. Now this is f of x is equal to 2x minus 3x to the 2/3 power. All right, now once again, when I say find the maximum or minimum, we're talking about the absolute maximum or minimum, right? Over the closed interval from negative 1 to 3. So closed interval, you got to check the endpoints. Like I said, I teach AP Calculus, and one of the big mistakes that students make on the AP Calculus exam, if they're asked to find a maximum or minimum value, they'll forget to check the endpoints. Right? They'll just find the critical numbers, set the derivative equal to 0, and then solve for x. And they'll forget to check the endpoints, but you got to check the endpoints. If it's a closed interval, the endpoints can be absolute maximum or minimum. Now, so let's try this problem here. This is over the interval from -1 to +3. Okay, so to get us started, now I'm going to start off, let's go ahead and get the derivative. We're going to have to eventually, so we're going to get the derivative first. Now the derivative here would be derivative of 2x is 2 minus, now the derivative of 3x to the 2/3. 2/3 times 3 gives us 2, so we minus 2x. Remember now, you've got to subtract 1 from your exponent as you take that derivative. Now 2/3 minus 1 would give us -1/3. So we're going to rewrite the derivative like so. This will be equal to 2 minus 2 over x to the 1/3 power. So this is our derivative. Now, let's go ahead and check the endpoints. So we're going to do the endpoints first, and then we'll check see if we have any critical numbers, and we'll check those. All right, so let's do the endpoints next. Let's see, so for our endpoints, so let's check our endpoints. Okay, let's take the, we'll start with the -1. Let's take the -1 and plug it into the original function. So f of -1, this will be 2 times -1 minus 3 times -1 to the 2/3 power. Okay, now 2 times -2 is, 2 times -1 is -2 minus. Now -1 to the 2/3 power would make that a +1 times -3 would be just -3, so this would be -5. Right, so our first endpoint here would be at -1, -5. So that'll be our first endpoint. Now the second endpoint was at 3, so the function at 3 would be 2 times 3 minus 3 times 3 to the 2/3 power. All right. Now as you evaluate this now, so as you evaluate the 3, as you substitute the 3 in, this will give us gives us a decimal, so we end up with a -0.240, right? So this particular endpoint would be at the ordered pair of 3 and then -0.240, so -0.24. Right, so you get this radical here. So I just did this on my calculator so I can see, so you can compare the two. Now once again, before we do the critical numbers now, okay, let's compare the y values of our two endpoints. You got one y value is at -5, the other one is at -0.2. All right, so right now, -5 would be the minimum, -0.2 would be the maximum. All right, now we still got to check the interior of the graph. Now, when you do the interior, we're looking for the critical points now. So let me set this over to the side. Okay, now let's see. Now this time, to get our critical numbers, we're looking where our critical numbers. We're talking about where the derivative is equal to 0 and where the derivative does not exist. So you always got to check both of these. So where does the derivative equal to 0? Where does it not exist at? Right. Now, as you look at the derivative here, we got 2 minus 2 over x to the 1/3 power. Now, you recognize immediately the derivative has a fraction in it. The bottom of a fraction cannot equal 0. So the derivative does not exist where x to the 1/3 is equal to 0. Now, so it does not exist where x to the 1/3 is equal to 0. Now, to get rid of a 1/3 power, you're going to take the cube root of both sides. So take the cube root, we know that x equals 0. So our first critical number is that x equals 0. Now, make sure that 0 is within your interval now. We're in the interval from -1 to 3. 0 is within -1 and 3. So that's going to be our first critical number. A possible maximum or minimum, all right, so we'll see. Now let's see where the derivative is equal to 0. Now to get the zeros of the derivative, this time we'll take the entire derivative. So set it equal to 0. So 2 minus 2 over x to the 1/3 power. Now we're going to solve this equation for x now. Now let's bring the 2 to the left-hand side. That gives us -2 equals -2 over x to the 1/3. We'll drop the negative off each side. And we end up with +2 equals +2 over x to the 1/3. Now I'm going to multiply. Remember, we have to get, when you see a fraction, a variable in the bottom of a fraction, you got to get the variable out of that fraction. So to get rid of that x to the 1/3 on the bottom of the fraction, Okay, we're going to multiply x to the 1/3 to that side, and you got to multiply x to the 1/3 to the left-hand side. That gives us 2x to the 1/3 equals 2. So to get that variable at the bottom of your fraction, a fraction is just division. To get rid of division, you multiply. Now to finish this up, we're going to divide both sides by 2. That gives x to the 1/3 is equal to 1. Now to get rid of the 1/3 exponent here, we're going to cube both sides. So the cube, as you multiply here, that gives us just x equals 1 to the 3rd power is 1. So this is our other critical number. So 2 critical numbers here. So we got 0. Now once again, as you look at this, make sure that the 1 is within your interval, and ours is. So 1 and 0, both critical numbers are within their interval from -1 to 3. So let's check each of those. Now you got to check them in the original function, because remember now we got to be able to compare our y values. Okay, this is the x values. All right, so we got to be able to compare our y values to these 2 y values on our endpoint now. So we got 1 and 0. So let me erase this up here. So x equal 1. Okay, x equals 0. So let's take each of those. Let's substitute them in. Let's see what we get. All right. Let's see. We'll do the 0. So we'll do the 0 first. That'll be pretty easy. So f of 0. Okay, this is 2 times 0 minus 3 times 0 to the 2/3 power gives us a 0. So our first critical number, our first critical point this time is at 0, 0. Remember, x equals 0 is the critical number. The point 0, 0 is the critical point. So you're talking about a 0, 0. It's possible. This could be a possible absolute maximum, absolute minimum compared to the others here. Okay, let's substitute the 1 into the original function now. So this will be f of 1. Okay, this will be 2 times 1 minus 3 times 1 to the 2/3 power. Okay, and then 2 times 1 gives us, so it gives us what? 2 minus 3, which would be -1. So this would be the point 1, -1. All right. Now, once we get both of our critical points, we've got our endpoints over here. Let's compare. We're going to compare the -5, the -0.24, okay, the 0, the y value of your critical point, and the y value of the other critical point. So as you compare each of these, so first thing you notice now, let's see, -5 here looks to be the minimum, doesn't it? So we got -5, -0.2, you got 0 and -1. So it looks like this one right here would be so -5 would be the absolute minimum. So that's the absolute minimum. Now the maximum would be, so that would be the minimum, so -0.2, -1, and 0. Looks like 0 here is going to be the maximum. So 0, 0 is the maximum. And it looks like -1, -5 is the absolute minimum. So if you look at, remember, on a closed interval like this, you will always have a maximum minimum. As long as the graph is continuous, you must have a minimum and a maximum. These are both absolute. There's no place on the curve higher than 0, 0, and there's no point on the curve lower than -1, -5. So that's what that means. Okay, we'll do one more example. And we did let's try a fraction this time. So fractions tend to give students a little bit of trouble. So we'll try a fraction, and we'll finish up with the fraction. Let's erase this. And once again, we're looking for the absolute minimum, absolute maximum. Let's erase this. There we go. And let's go ahead and bring up our next problem. Here we are. Okay, here we go. Now, it says, now this time our function, we got the function x over x plus 3 over the interval from -1 to 6. So let me go ahead and write our function down up here. So h of x is equal to, this is number 6. So h of x is equal to x over x plus 3. This is over the interval from -1 to 6. That has to be closed here. There we go. So -1 to 6. Now, let's start off by getting the derivative. I mean, you can get it now, you can get it later, but you're going to have to find the derivative when we do our critical numbers. All right, so let's go and get the derivative. Now, to get the derivative, this is a fraction, so we're going to have to use the quotient rule again. All right, so as we get our derivative, this will be h prime x will be equal to, this will be x plus 3 quantity squared. So x plus 3 quantity squared. And this will be the bottom, x plus 3 times the derivative of the top. Now the derivative of x is 1 minus the top times the derivative of the bottom. Now the derivative of x plus 3 is 1. Okay, this is our derivative. Now as we simplify this now, this will give us x plus 3 minus x on top of our fraction, and this will be x plus 3 to the second power on the bottom of the fraction. Now the x's add up to 0, and our derivative becomes, so simply 3 over x plus 3 to the second power. So this is our derivative. Okay, well, let's go ahead and do the endpoints. All right, so let's check the endpoints and see what we get this time. So let's do the endpoints. Okay. So to begin, let's do the negative one first. Remember, we're going to plug the endpoints into the original function. Remember, we've got to check the y values. So substituting negative 1 in for x first, so h of negative 1 gives us negative 1 over negative 1 plus 3, which is negative 1/2. So this will be the ordered pair negative 1, negative 1/2. So that's our first endpoint. So negative 1, negative 1/2. Let's try the second one. So h of 6 will be 6 over 6 plus 3, which would be 6 over 9, which is 2/3. All right, so the other endpoint is going to be at 6 and 2/3. All right. Now, just comparing their y values, we got one y value is negative 1/2. The other y value is 2/3. So 2/3 would be the maximum, negative, and then negative 1/2 would be the minimum. So if you were just looking at the endpoints, that's how they would play out. Okay, let's get our critical numbers now. So let me set this over out of the way. Now for the critical numbers, let me erase this. And so our critical numbers, we're looking where the derivative is equal to 0 and where the derivative does not exist. All right. Now we got that. As I look at the derivative here, right away you recognize that the derivative is a fraction. The bottom of the fraction cannot be 0 or it won't be defined. So we're going to find the zeros of the denominator. So x plus 3 squared equals 0. So remember, if you're checking to see where it doesn't exist, you take just the bottom of the fraction only, set that equal 0. All right? And let's see what we get. Now start off, as you solve this for x, you've got to take the square root of both sides. That gives x plus 3 is equal to 0. This gives x equals negative 3. So our first critical number. Now let's check it to make sure that it's within our interval. Well, we have a problem. You guys notice negative 3 is outside the interval from negative 1 to 6. So this one we don't have to worry about. That's outside the interval. Right, so we don't have to worry about the negative 3. That's pretty good. Right, so that one's outside the interval. So outside the interval. Right, so now if you're not watching for that, you could go ahead and check that into your original function, and you could mistakenly claim that it's a maximum or minimum, and it's not. It's outside our interval. Now let's find where the derivative is equal to 0 now. So we possibly have a horizontal tangent line. All right. So we're going to take the entire derivative, set that equal to 0. So 0 equals 3 over x plus 3 to the second power. So remember now, when you find where the derivative doesn't exist, you take the bottom of the derivative only. If it's a fraction, you take your denominator, and you're going to find the zeros of your denominator. If you're finding where the derivative itself is equal to 0, you've got to take the entire derivative function and set that equal to 0 and solve this for x. Now, multiplying x plus 3 squared to both sides gives us 0 equals 3. Now, here's another problem. 0 equals 3, there's no solution for this one, so no solution. All right, now that tells us that, that the negative 3 is outside the interval. We don't have to worry about it, and there's no solution where the derivative is equal to 0 on this particular interval. So, there's no critical numbers we have to worry about with this problem. So that means in this problem, the absolute maximum, absolute minimum must be at the endpoints. So let's check them just like we indicated a minute ago. Okay, this is going to be the minimum. And 2/3 is going to be the maximum. So negative 1/2 will be the minimum. It occurs at x equal negative 1. The absolute maximum is at 2/3 and it occurs at x equals 6. Okay, thank you for watching our video. Hopefully you found some of these examples helpful.